Hello, everybody. Sierra, Tristan, Helen, Sylvia, Jonah, Rebecca. Good to see you all here. Today, we're going to take a look at something called implicit differentiation, which is a direct offshoot of the chain rule, which is why not only do I do it after the chain rule, but I stop and pause and give you a gateway quiz and make sure that we're good with the chain rule before we move on. I'll try to keep this fairly quick. We'll definitely go over some more examples of this on Thursday, but here is a brief introduction. All right, so we're doing implicit differentiation. And you probably weren't even aware that up until this point, we've only done explicit differentiation. In other words, differentiation of equations where I've got one variable or a function explicitly solved for, y in terms of x, area in terms of radius, f of x, h of t, one variable. The output is a function of a variable. And so find the derivative of the function in terms of x. Find dy dx. And so what we're going to do today is change the type of equation we are differentiating. We're going to do something called implicit differentiation, which basically means I don't need to have y equals or h equals or a equals or just something in terms of one other variable. As you can see, the green equation I have here, it's x equals, but it's x in terms of both x's and y's. We've got them intermixed. Here we've got the equation of a circle, x squared plus y squared equals r squared. Yes, I could solve for y and then take the derivative, but we'll find out that implicitly solving or finding the derivative is a little bit easier. And then likewise here, try to solve this for y or solve it for x in terms of the other variable, and you will not be able to. I wouldn't be able to either, and that's okay. That's what we're going to find out. We can just take a derivative as is. The big idea here is that the chain rule still applies. The derivative of f of something is f prime of the something times the derivative of the something, the stuff inside. The derivative of sine of something is cosine of something times the derivative of the something. The derivative of the square root of something is 1/2 times the something to the negative 1/2 times the derivative of the something. The chain rule still applies. And so when I have an equation, or I guess in this case, an expression, I've got just x plus y, and I say take the derivative in terms of x. Well, term by term, I can go through and say, what is the derivative of x in terms of x? You could call this dx dx plus the derivative of y in terms of x. And we're going to call that dy dx. Now, dx dx, how fast is x changing in terms of x? The rate of change of x with respect to x is just 1. The rate that x is changing with respect to how fast x is changing, well, it's the same thing. Dx dx is just 1. And I'll refer to that a little bit more in just a moment. And then dy dx, how fast is y changing? And so I'm taking the derivative of two different variables, x and y, in terms of one of those variables, and I'm getting an expression that looks like this. Here's that equation of a circle, x squared plus y squared equals r squared. And so if I say find dy dx, now dy dx is still the slope of a tangent line to this curve, this circle in this case. But what we're going to find is that when I solve for the derivative dy dx implicitly, we'll have this derivative not just in terms of x, but in terms of x and y. A circle is not a function, so it won't just be in terms of x, it'll be in terms of both x and y. It'll be in terms of a location in space. And so when I take the derivative, find the derivative in terms of x, I'm going to say let's do the derivative in terms of x of this x squared plus y squared. And sorry, my writing is bordering on illegible when I have to use the mouse like I'm using right now, but hopefully my narration will help us to hear what's going on or see what's going on. So the derivative. I'm taking the derivative in terms of x. And so the derivative of x squared in terms of x, well, that's what you've been doing for a couple weeks in this class. What's the derivative of x squared in terms of x? That's just 2x, just like it's always been. The derivative of y squared, well, the derivative of something squared is 2 times the something, 2y in this case, times the derivative of the something. Now, the derivative of the x, we just kind of overlook because the derivative of x in terms of x is just 1. dx is just 1. But dy dx, how fast y is changing with respect to x, well, that isn't just 1. That's dy dx. Change of y with respect to x. Now, later on in this chapter, actually in the last unit or the last section in this chapter, we'll take a look at what happens if the radius of the circle is also changing. I've got a circle and the radius is increasing at a rate of, 1 unit per second or whatever it is. And we will do stuff like that. But at least for right now, I'm going to treat this r as a constant. I've got a circle with a radius of 5. It's a constant. And so my derivative of r squared, well, just like the derivative of pi squared, the derivative of e squared, the derivative of r squared is just 0. And so there we go. We have implicitly differentiated this equation for a circle. But if I want to find dy dx, or if I say solve for dy dx, now this becomes an algebra problem. I want to solve for dy dx. So just like if this is a variable that I'm solving for, I'm going to subtract 2x from both sides of this equation. I get 2y dy dx equals negative 2x. And then I'll divide both sides of this equation by 2y to isolate dy dx, to get dy dx all by itself. And so at this point, I can't see. Sorry, I'm not sure what this is going to look like with video when I change my window. Hopefully that was not too weird. Now I've got dy dx equals, well, negative 2x over 2y. I'm going to cancel out those 2's and say that this is negative x over y, which is kind of interesting. So on a circle centered at the origin, x squared plus y squared equals r squared is a circle with a center at 0, 0 at the origin with a radius of r. So apparently to find the slope of a tangent line anywhere on that circle, I can just take the opposite of the x coordinate divided by the y coordinate. Let's take a look at an example. Here is a circle with a radius of, looks like about 8. And so if I look at the tangent to the curve up here at the top, at the point 0, 8, according to what we just found, the slope of the tangent line there is going to be the opposite of the x value divided by the y value. In this case, negative 0 divided by 8, but 0 divided by 8 is just 0. And so, as we would expect, the slope of a tangent line here is just going to be 0. If I look at, let's see, I'm going to try to find a point where it looks like it's pretty close to some grid points. Let's see, this would be the point 1, 2, 3, 4. This is 5, 6. Now we would expect that the slope of a tangent line is going to be negative. It looks like it's not quite negative 1. It's something a little bit less than negative 1. And sure enough, my formula for the slope of a tangent line is the opposite of x over y. It looks like the slope at that point of a tangent line would be negative 5/6, just as you would expect. A point back here at negative 8, 0, our equation predicts that the slope of a tangent line would be the opposite of negative 8 divided by 0. So positive 8 divided by 0, but that doesn't exist. And that makes sense because I've got a vertical tangent at that point. Something I find interesting about this is that it doesn't matter what the radius of the circle is. I just happen to have a circle with a radius of 8, but if the radius was 1 or if the radius was 10,000, this formula still works. It is independent of the radius, which is, I don't know, I think kind of a cool thing. I want to do just one more quick example. So those of you who want to take a look at some of the problems in the textbook before we see each other again on Thursday will be able to do so. Here, clearly, I've got a more complicated example, and I don't even know what this looks like. I honestly just kind of made up some coefficients and put some powers on this just so we'd have something to think about. When you see something like this, keep in mind the product rule. I've got 2x, which I know how to differentiate, times y squared, which I know how to differentiate. In that last term, I've got 4x cubed, which I know how to differentiate, times y, which now I know how to differentiate. And so as I take my derivatives, I'm going to do product rule. 2x times the derivative of y squared. Well, the derivative of something squared is 2 times the something times the derivative of the something. And the derivative of y, I'm going to call dy dx. So there's the first times the derivative of the second. I'll do plus the derivative of 2x, which is 2, times y squared. There we go. So product rule has gotten me through that first term, minus the derivative of x. Well, that's just 1, just like it's always been. Now we kind of see the hidden man behind the curtain who says the derivative of 1x is 1 times the derivative of x, but the derivative of x is just 1. On the right side, I've got the derivative of y to the 5th power. Well, the derivative of something to the 5th power is 5 times the something to the 4th power, times the derivative of the something. Derivative of y, I would call dy dx. And then minus, I'm going to put a big parenthesis here because I'm subtracting the derivative of this product, and I don't want to miss out on any terms. So I will have 4x cubed times the derivative of y. I'll call that dy dx. And then the other half of the product rule, the derivative of 4x cubed is 12x squared times y. I suppose you could think of it in terms that if you take the derivative of an x term, it's the same derivatives that we've been doing for a while in this class. If you take the derivative of a y term, just tack on that dy dx at the end. And that's not too bad, but it does come from the chain rule, so don't lose sight of that. And now if I want to solve this equation for dy dx, I want to isolate those dy dx. This looks like a really nasty algebra problem, but it's actually not all that bad. First thing I'm going to do is combine 2x times 2y, I'm going to call that 4xy dy dx. 2y squared, I guess I can't do too much with that. I've got minus 1, can't do much there. Really, there's not a whole lot that I can do with this first simplification step, so I'll just keep going through this. And like I said, this is looking kind of ugly. Yikes, how are we supposed to solve an equation like this that has dy dx's sprayed all over the place, and I'm supposed to get those all together and solve for dy dx? Well, what it boils down to is that when you do a problem like this, when we do this derivative, no matter how nasty this is, once I have a bunch of terms, I've got some terms that have a dy dx in them, and I've got some terms that don't. And so what I'm going to do next is just isolate the terms that have dy dx on one side of the equation and put all the other terms on the other. It really doesn't matter which way I do this, but I notice that I've got 2 terms with dy dx on the right side already, so I'll just keep those there, and I'll subtract this 4xy dy dx term over to the right side. Likewise, I've got 2 terms on the left side that don't have dy dx and only 1 on the right side that doesn't. So I'll subtract this 12x squared y term from both sides, and I'll also subtract this 4xy dy dx term so that all of my dy dx terms will be on the right side. I'll have 5y to the 4th dy dx minus 4x cubed. Not really doing anything so far except copying them down. But now I'll subtract that 4xy dy dx term. So all of my dy dx terms are on the right side. On the left side, I've got that 2y squared minus 1 that's already there. And then I'll subtract that 12x squared y. So what I've done at this point is I've isolated, we could think of them as like terms. Dy dx is on one side of the equation, terms that don't on the other side. If I was with you, I would suggest, what can we do since all of the terms have dy dx on the right side? And someone would bravely raise their hand and say, let's factor out that dy dx. And I'd say, thank you for that idea. That's a wonderful idea. I'll be left with 5y to the fourth minus 4x cubed minus 4xy. And so if I'm solving for dy dx, I only have one step left here. I've got all of this stuff, these three terms that are multiplied by dy dx. I'm just going to divide both sides of this equation by those three terms. And so I'll end up with, here is my expression, dy dx. You want to amaze your friends, show them what you're doing. This looks really complicated, even though it's really just a little bit of algebra, subtracting, combining like terms, moving everything to one side of the equation. So dividing by 5y to the fourth minus 4x cubed minus 4xy. And there we go. I have found the slope of a tangent line to this crazy curve. Go ahead and throw it in Desmos and see what it looks like, though it probably actually isn't all that interesting. And you can find the slope of a tangent line to the curve by plugging in the coordinates for any point that is on this curve. I think that's probably enough. We're certainly not done with this. I've got some other things that I want to take a look at, including what happens if I take the derivative of x in terms of y instead of y in terms of x. What happens when we have follow-up questions. Where are their horizontal tangents? Where are their vertical tangents? Where is the tangent line parallel to this other line? But I'm going to save those for when I am back with you on Thursday. So hopefully this gives you something to think about. Go ahead and get started on the assignment, but I'll make the implicit differentiation assignment due on Friday. So we'll have a chance to work together on Thursday. Have a great day. I will see you all on Thursday. Hope you all rested and are well rested and ready to learn on Thursday, since you all got to sleep in while I was proctoring the pre-ACT on Wednesday. Have a great day. See ya. Bye.